What if I told you that everything we think we know about the universe might be built upon a fundamental misunderstanding? For nearly a century, astronomers have been grappling with a cosmic mystery so profound that it challenges the very foundations of physics. Galaxies should be flying apart, stars should be scattering into the void, yet something invisible holds them together with unimaginable strength. We called this mysterious force dark matter, giving a name to the unknown while believing we understood its nature. But what if dark matter isn't what we thought at all? Picture our universe as a grand cosmic tapestry, woven with threads of light and matter that we can observe and measure. Yet hidden between these threads are forces so subtle, so elusive, that they've remained virtually undetectable despite decades of searching. The conventional view of dark matter as simple, sluggish particles now appears increasingly inadequate to explain the strange behaviors astronomers are documenting across the cosmos. From galaxies that rotate with impossible symmetry to cosmic structures that formed too quickly after the Big Bang, the evidence is mounting that our current models are missing something extraordinary. Today, we're embarking on a journey to the very frontiers of cosmological discovery, where revolutionary ideas are challenging decades of established science. We'll explore how new research is revealing unseen forces that operate in ways we never anticipated. Forces that might completely rewrite our understanding of gravity, matter, and the fundamental workings of reality itself. This isn't just about updating a scientific theory, it's about rediscovering the universe through new eyes and confronting the humbling possibility that the cosmos holds secrets far stranger and more wonderful than we ever imagined. The story of dark matter begins not with a grand announcement, but with a stubborn anomaly that refused to be explained away. In the 1930s, a brilliant and often contentious astronomer named Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies millions of light-years away. By measuring how these galaxies moved in relation to one another, Zwicky could estimate the cluster's total mass. What he found was utterly perplexing. The galaxies were whipping around at such incredible speeds that the gravitational pull from all the visible stars and gas should have been completely insufficient to hold the cluster together. By all rights, the entire system should have flown apart, scattering galaxies into the emptiness of space. The only logical conclusion was that there had to be far more matter present than anyone could see, matter that emitted no light. He gave this invisible substance a name that has echoed through astronomy ever since, Dunkel Materie, or dark matter. Yet, as often happens with ideas that are too far ahead of their time, Zwicky's proposal was met with skepticism and largely ignored for decades. The astronomical community wasn't yet ready to accept that the universe was dominated by something we couldn't observe. The puzzle remained a curious footnote until the 1970s, when an astronomer named Vera Rubin provided the undeniable evidence that would force science to confront this cosmic secret. Rubin was meticulously mapping the rotation of spiral galaxies, expecting to confirm what Newtonian physics predicted, that stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly than those closer in. Think of our solar system. Pluto, way out on the edge, moves at a snail's pace compared to Mercury, which races around the Sun, but that's not what Rubin's data showed. To her astonishment, she found that stars at the very outskirts of these galaxies were orbiting just as fast as those near the center. It was as if every star, regardless of its distance, was experiencing the same immense gravitational pull. The only way this could be possible was if each galaxy was enveloped in a massive, spherical halo of some unseen material, providing the extra gravity needed to keep those high-speed stars from being flung into the void. This confirmation of Zwicky's initial hunch was a seismic shift in cosmology. Dark matter was no longer a fringe idea. It became the essential ingredient, the invisible scaffolding upon which the entire visible universe was built. It elegantly explained not only galaxy rotations, but also how massive structures formed after the Big Bang, and how light bends around galaxies in the phenomenon known as gravitational lensing. For decades, this model of cold, slow-moving dark matter particles has been the reigning theory, a cornerstone of our understanding. But this very history, this journey from ignored anomaly to established doctrine, contains a crucial lesson. It reminds us that science progresses not by clinging to comfortable ideas, but by relentlessly investigating the next anomaly, the next piece of data that doesn't quite fit. And that is precisely where we find ourselves today. So let's break down exactly what this established model tells us. Think of the universe as being filled with two fundamentally different types of stuff. The first is the ordinary matter that makes up everything we can see and touch: planets, stars, galaxies, and even our own bodies. This baryonic matter, however, is astonishingly rare, constituting less than 5% of the universe's total mass and energy. The rest, the overwhelming majority, is this dark, invisible component. About 68% is something we call dark energy, which is responsible for the accelerating expansion of the universe. And the remaining 27%, the true subject of our mystery, is dark matter. This dark matter is not just simple dust or gas that's too cold to see. It's something far more exotic. The leading theoretical candidate for decades has been a class of particles known as WIMP, or weakly interacting massive particles. The name itself tells you almost everything about their proposed nature. Massive means they have substantial heft, likely many times heavier than a proton, which is why their collective gravity is so overpowering. Weakly interacting is the crucial part. It means these particles ignore almost all the forces that govern our everyday lives. They don't feel the electromagnetic force, so light simply passes right through them, rendering them completely invisible. They don't participate in the strong nuclear force that holds atomic nuclei together. Their only confirmed method of interaction is through gravity, which is how they sculpt the cosmos, and they might occasionally interact via the weak nuclear force, which is responsible for certain types of radioactive decay. This standard model of cold, collisionless dark matter has been a workhorse of modern cosmology. Its gravitational influence provides the essential scaffolding for the universe. Without it, the primordial soup of particles after the Big Bang would not have clumped together fast enough to form the magnificent web of galaxies and galaxy clusters we observe today. Its gravitational pull perfectly explains the anomalous rotation curves of galaxies that Vera Rubin measured, and the way its immense mass bends the fabric of space-time, acting as a cosmic lens to distort the light from objects behind it. On the largest scales, the model is a resounding success, yet for all its predictive power on a grand scale, this very success hinges on a profound irony. We have never directly detected a single particle of it. For over 30 years, physicists have been conducting increasingly sensitive experiments deep underground, in abandoned mines and tunnels, shielded from cosmic rays. These detectors are designed to catch the incredibly rare and faint shudder that would occur if a WIMP particle ever bumped into the nucleus of an atom in a vat of ultra-pure xenon or germanium. Despite this monumental effort, the result has been a deafening silence. Not one unambiguous signal has been found. This absence of evidence is becoming harder and harder to ignore, forcing a moment of collective introspection within the scientific community. The persistence of this null result isn't just a minor setback. It's a growing crack in the foundation of our understanding, a silent hint that the universe's deepest secrets may be governed by rules we have yet to imagine. This galactic rotation problem became the cornerstone of the dark matter hypothesis, a puzzle so compelling it reshaped cosmology. To truly grasp why this was such a monumental discovery, we need to step into the mind of an astronomer and understand what they expected to see. The rules of orbital mechanics, laid down by Newton and refined by Einstein, are incredibly reliable. We use them to perfectly plot the course of spacecraft to distant planets and to predict the dance of binary star systems with astonishing accuracy. So when we apply these same trusted rules to an entire galaxy, the result should be a very specific pattern. Imagine a giant merry-go-round. If most of its mass is concentrated at the center, a child sitting on an outer horse has to hold on much tighter to avoid flying off as the ride spins. That child is moving much faster than another child sitting closer to the center, who experiences a gentler spin. This is exactly how our solar system works, with inner planets like Mercury racing around the Sun while outer planets like Neptune plod along on a far slower, more sedate path. Now apply that logic to a spiral galaxy like our own Milky Way. The vast majority of its visible mass, all the stars, gas, and dust we can see, is concentrated in the bright central bulge and the disk. According to every known law of physics, a star orbiting far out in the galactic suburbs, tens of thousands of light years from the crowded center, should be experiencing a much weaker gravitational pull. To maintain a stable orbit at that distance, it must move more slowly. If you were to graph this, plotting a star's orbital speed against its distance from the galactic center, you would expect to see a beautiful, clean curve. The speed would rise quickly as you move out from the center, peak near the edge of the central bulge, and then fall off sharply in a steady decline. This is known as a Keplerian decline, named for the astronomer Johannes Kepler. But when astronomers like Vera Rubin actually measured this, the data told a completely different and utterly baffling story. They found that after an initial rise, the rotation curve didn't fall off. It flattened out into a straight line. Stars tens of thousands of light years out in the dark, sparse outskirts of the galaxy were hurtling around at nearly the same breakneck speed as those nestled deep within the bright, massive core. It was as if every child on that merry-go-round, regardless of how close they were to the center, was whirling around at the exact same velocity. The only possible explanation was that our map of the galaxy's mass was catastrophically wrong. The gravity holding those outer stars in place wasn't coming from the material we could see. It had to be emanating from a vast, spherical halo of something invisible, enveloping the entire galaxy like a ghostly cocoon. This was the dark matter halo, and its gravitational signature was undeniable. The evidence became even more robust with the advent of powerful computer simulations. When cosmologists programmed the laws of physics and the known initial conditions of the early universe into supercomputers, and then added this cold, collisionless dark matter as the dominant ingredient, something remarkable happened. These virtual universes evolved over billions of simulated years and produced galaxies that looked and rotated exactly like the ones we observe through our telescopes. The simulated rotation curves matched the real, flat ones perfectly. This wasn't just a single observation anymore, it was a successful prediction of an entire model. The dark matter paradigm didn't just explain the data, it could recreate it from first principles, a powerful testament to its explanatory power. Yet even as this model cemented itself as the standard theory, small cracks began to appear around the edges. Not every galaxy fit the mold perfectly. Astronomers discovered a handful of puzzling outliers, galaxies that seem to have either too much or too little of this dark stuff based on their rotation. Some ultra-diffuse galaxies appeared to be almost entirely made of dark matter, while others, perplexingly, seemed to have almost none at all. The most intriguing anomalies were a class of galaxies whose rotation curves didn't just flatten out, but showed tiny, specific wiggles and dips that corresponded exactly with the distribution of their visible matter. It was as if the gravity in these places was precisely where the stars and gas were, not smeared out in a giant, smooth halo. These weren't massive inconsistencies that overthrew the whole model, but they were nagging questions, subtle whispers from the cosmos that perhaps the story was more complicated than we had assumed. They were the first clues that sent scientists back to the drawing board, wondering if the universe was trying to tell us something entirely new about the fundamental nature of gravity itself. So if the evidence for dark matter's gravitational influence is so strong, why are we even considering alternatives? It's because the most elegant scientific theories are often the simplest ones that explain the most with the least. And the idea of inventing an entirely new, invisible form of matter that makes up 27% of the universe, a substance that has evaded every single attempt to directly detect it for decades, is by its very nature not simple. This persistent failure to find dark matter particles has opened the door for a radically different approach, one that asks a profoundly unsettling question. What if we haven't found dark matter because it doesn't actually exist? What if the problem isn't with the cosmos, but with our centuries-old understanding of gravity itself? This is the brilliant, controversial, and utterly fascinating premise of modified Newtonian dynamics, or MOND. Proposed in the early 1980s by Israeli physicist Mordechai Milgrom, MOND is the ultimate scientific Occam's razor. Instead of populating the universe with trillions upon trillions of unseen particles, Milgrom suggested a single, elegant tweak to the laws of physics. He posited that Newton's second law of motion, F equals ma, which we've accepted as gospel since the 1600s, might break down at extremely low accelerations. This isn't as wild as it sounds. Einstein's theory of general relativity already showed us that Newton's laws aren't the final word. They break down in extreme gravitational fields, like near a black hole. Milgrom simply proposed another frontier where they might fail, in the realm of the incredibly faint. Think of it this way: the gravitational pull a star feels out in the lonely outskirts of a galaxy is almost unimaginably weak. It exists in a regime of acceleration so low that it's equivalent to just a billionth of the gentle tug you feel from Earth's gravity right now. Milgrom's crucial insight was that perhaps our tested laws of motion don't apply in this ghostly realm of the infinitesimal. He proposed a new threshold, a critical acceleration below which gravity begins to behave differently. Above this threshold, in places like our solar system where accelerations are high, Newton and Einstein rule supreme, and their predictions work perfectly. But below it, in the deep gravitational darkness between stars and galaxies, the force of gravity becomes stronger than the standard laws would predict. This single modification produces a breathtaking result. When you recalculate the expected rotation of a galaxy using MOND-adjusted formula, the need for a dark matter halo simply vanishes. The mathematics naturally produces a flat rotation curve, perfectly matching Vera Rubin's observations without a single invisible particle. The stars on the outskirts are moving faster because the gravitational force holding them is, according to this new law, stronger than we thought. It's not extra matter providing the pull, it's a fundamental change in the rules of the game. Where MOND truly shines, and what has kept it in the scientific conversation for over 40 years, is its astonishing predictive power. While the dark matter model often requires complex, after-the-fact adjustments to explain the behavior of certain galaxies. MOND has repeatedly made bold, specific predictions that were later confirmed by observation. For certain types of dwarf galaxies and low surface brightness galaxies, MOND predicted their exact rotation curves based solely on the distribution of their visible mass. In many cases, it was right where the standard dark matter model was wrong or needed cumbersome explanations. This predictive success is the lifeblood of any scientific theory, and it's the primary reason MOND cannot be easily dismissed. However, for all its elegance and success on the galactic scale, MOND faces its own monumental challenges. The theory was specifically crafted to solve the galaxy rotation problem, and it excels there. But the universe is a much bigger and more complex place. When we zoom out to the scale of massive galaxy clusters, the gravitational lensing effects are so powerful that they seem to require far more mass than MOND can provide, even with its modification. The observed motions of galaxies within these vast clusters also seem to demand more gravity than MOND formulas can muster. On the largest cosmological scales, like the pattern of the cosmic microwave background radiation, the afterglow of the Big Bang, the standard model of cosmology with dark matter provides a near-perfect fit, while MOND in its original form falls short. It's as if this elegant solution works beautifully for the individual trees but struggles to describe the entire forest. This has led to a fascinating evolution in the field. The conversation is no longer a simplistic battle between dark matter and MOND. The most intriguing developments are hybrid ideas that attempt to capture the best of both worlds. Some theorists are working on relativistic extensions of MOND, frameworks that could apply across the entire universe and potentially address these larger-scale issues. Others are exploring theories where a light, interacting field permeates space, effectively producing a MOND-like behavior without completely abandoning the concept of an additional cosmic component. These aren't just stubborn alternatives, they are creative, rigorous attempts to grapple with the full spectrum of data, reminding us that the path to discovery is rarely a straight line. Just when the cosmological community had settled into a comfortable consensus, the universe delivered another stunning surprise, one that seemed to flip the entire dark matter narrative on its head. For decades, the central pillar of the theory was that dark matter was not just common, but absolutely essential, the universal glue holding every galaxy together. The very definition of a galaxy, according to this view, was a luminous collection of stars swimming within a much larger, invisible sea of dark matter. This idea was so fundamental that it was treated as a cosmic law, but in science, it's often the exception, the single outlier that doesn't fit, that forces a true revolution in thinking. This revolution began with the discovery of a ghostly, enigmatic class of objects known as ultra-diffuse galaxies. These are not the majestic, star-packed spirals we're familiar with. They are vast, wispy, and incredibly faint, like cosmic jellyfish drifting through the blackness of space. Their stars are so thinly spread that you could look right through them. And among these faint ghosts, astronomers using sophisticated instruments like the Dragonfly telephoto array began to find something truly bizarre. Galaxies that, by all rights, should not exist at all. The most famous and perplexing examples are a pair known as NGC 1052 DF2 and DF4, located about 65 million light-years away. When a team led by astronomer Pieter van Dokkum measured the motions of their star clusters and globular clusters, they expected to see the telltale signs of a massive dark matter halo at work. Instead, they found something that sent a shockwave through the field of cosmology. The stellar motions were slow, sedate, and perfectly predictable. When they crunched the numbers, they made a staggering realization. The total mass of these galaxies, calculated from the star's velocities, was almost exactly equal to the mass of all the visible stars and gas they could see. There was no extra mass, there was no dark matter. This was a result so counterintuitive, so utterly contradictory to decades of established theory, that the initial reaction from many was sheer disbelief. It was the equivalent of finding a car with no engine somehow speeding down the highway. How could a galaxy form, or even hold itself together, without the immense gravitational anchor of a dark matter halo? The Standard Model had no ready answer. If dark matter is a ubiquitous particle that pervades all of space and guides the formation of all structures, how could some galaxies mysteriously lack it entirely? This paradox cuts to the very heart of the matter, presenting a challenge that is far more profound than it might first appear. One immediate line of thinking was that perhaps these galaxies didn't form without dark matter, but somehow lost it. The leading hypothesis suggests a violent cosmic encounter. Imagine two nascent galaxies, each with its own healthy halo of dark matter, beginning to merge. As they pass through each other, their clouds of dark matter, which rarely interact, might simply pass through one another and keep going. The regular, baryonic matter, the stars and gas, feels a different set of rules. Gas clouds collide, create shock waves, and trigger bursts of star formation, effectively getting stuck in the middle of the merger. The result could be a new galaxy, born from this violent interaction, that is composed almost entirely of the visible stuff, while the dark matter from both parents has been flung out into intergalactic space, leaving its orphaned stellar children behind. It's a clever and dramatic story, but it raises a host of new and perhaps even more difficult questions. For this process to work, the initial conditions and the physics of the collision would have to be exquisitely precise, a perfect storm of cosmic events. If this is the explanation, then we should expect galaxies without dark matter to be incredibly rare oddities, the bizarre exceptions that prove the rule. Yet, as observational techniques improve, astronomers are finding more and more of them. Their apparent rarity might simply be a function of how difficult they are to detect. This suggests that if we could see all the faint galaxies in the universe, we might find that a significant population lacks dark matter, which would completely undermine the "lost it" hypothesis. Furthermore, finding two such galaxies, DF2 and DF4, in relatively close proximity to each other seems like an astonishing coincidence if they are both the unlikely products of separate, perfect collisions. The existence of these dark matter-deficient galaxies is more than just a curious anomaly. It strikes a deep blow at the predictive power of the Standard Model. A theory is at its strongest when it can clearly tell us what we should not find. For years, the dark matter paradigm implicitly argued that a galaxy without a dark matter halo was an impossibility. The discovery of DF2 and its siblings is a direct falsification of that prediction. It forces a monumental shift in perspective. We can no longer say that dark matter is strictly necessary for a structure to be called a galaxy. This doesn't disprove the particle idea outright, but it does demonstrate that the relationship between dark matter and visible matter is far more complex and nuanced than a simple, universal rule. This complexity is a gift to the proponents of modified gravity theories like MOND. For them, these strange galaxies are not a problem at all, they are a predicted victory. If the anomalous rotations of galaxies are caused not by invisible matter, but by a change in the laws of physics at low accelerations, then the amount of gravity a galaxy has is directly tied to the amount of visible matter it contains. A galaxy with very little visible matter should naturally have very little gravity, and its stars should therefore move slowly, exactly what we observe in DF2 and DF4. In the MOND framework, these galaxies aren't strange outliers. They are perfectly normal citizens of the universe, behaving exactly as the modified equations of motion say they should. They are the null hypothesis confirmed, a stunning validation that forces every cosmologist to stop and seriously reconsider the fundamental principles at play. The battle between these two explanations is no longer fought over which theory can explain the standard cases, but over which one can best account for the most extreme and puzzling exceptions the universe has to offer. While the rotation of galaxies provided the first major clue, the true power of the dark matter model is revealed when we watch light itself bend around the invisible. This incredible phenomenon, known as gravitational lensing, acts as a universal scale, allowing us to literally weigh the cosmos and map its hidden structures. According to Einstein's theory of general relativity, mass doesn't just create a gravitational pull, it warps the very fabric of spacetime around it. Imagine placing a heavy bowling ball in the center of a taut rubber sheet. The sheet will dip dramatically. Now roll a marble across that warped sheet. Its path will curve around the bowling ball, not because of a direct force, but because it's following the contours of the bent surface. Light behaves in exactly the same way. Even though it has no mass, a beam of light traveling through warped spacetime will follow the curves, causing its path to bend around a massive object. When that massive object is something like a galaxy cluster containing trillions of stars, the effect is magnified into one of the most spectacular sights in astronomy. The cluster acts as a colossal cosmic lens or a natural telescope, distorting the light from galaxies that lie billions of light years behind it. Sometimes this creates multiple smeared or stretched images of the same background galaxy, forming breathtaking arcs and rings of light known as Einstein rings. By meticulously measuring the precise degree of this distortion, astronomers can perform a kind of reverse engineering. They can calculate exactly how much mass the foreground cluster must contain to create that specific warping of light. Time and again, these gravitational lensing studies have delivered the same verdict. There is far more mass present than the sum of all the visible stars, gas, and dust. The only way to account for the extreme bending is to include a massive, smooth halo of dark matter enveloping the entire cluster. This technique has become the gold standard for proving dark matter's existence on the largest scales, providing a direct and seemingly irrefutable map of the invisible. Yet, as our telescopes have grown more powerful and our observations more precise, this clean picture has begun to develop intriguing smudges. Some of the most detailed lensing maps have revealed subtle but significant anomalies, places where the reality of the distortion doesn't perfectly match the predictions of the standard dark matter model. In a handful of systems, the lensing effect appears to be slightly misaligned or doesn't correspond exactly with the predicted distribution of the dark matter halo. It's as if the cosmic lens has a few tiny, unexpected imperfections in its glass. These mismatches are not enough to overthrow the entire model, but they are persistent enough to raise serious questions. Could these be hints that dark matter particles might interact with each other in ways we haven't accounted for, perhaps through some unknown force? Or could they be the faint signature of a deeper truth, a sign that our understanding of gravity itself needs refinement on these colossal scales? This is where the debate between particle dark matter and modified gravity becomes truly fascinating. Proponents of MOND and other alternative theories see these lensing anomalies not as problems, but as potential opportunities. They argue that if gravity is stronger at low accelerations, as MOND proposes, then it could naturally produce the right amount of light bending without needing to invoke vast amounts of invisible matter. Some relativistic extensions of MOND have been developed specifically to account for gravitational lensing, and they can, in certain cases, match the observations. However, the most massive galaxy clusters still present a formidable challenge for these alternative theories. The lensing effects there are so incredibly strong that they seem to demand a quantity of mass that modified gravity, in its current forms, struggles to provide. This has led to a new generation of hybrid models, where certain types of dark matter particles or fields are combined with a modification of gravity, creating a more complex but potentially more accurate description of the universe's scaffolding. The future of this entire field now hinges on a new era of sky-scanning observatories. The James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are not just taking prettier pictures, they are statistical powerhouses designed to collect lensing data on an unprecedented scale. They will measure the subtle distortions of billions of galaxies, allowing us to create the most detailed three-dimensional mass map of the universe ever made. This map won't just show us where the dark matter is, it will reveal how it clumps and evolves over cosmic time. Every tiny anomaly, every slight deviation from the expected model will be scrutinized. This flood of new data will either cement the cold dark matter paradigm by finally resolving the discrepancies, or it will uncover so many new puzzles that it forces a complete cosmological revolution, guiding us toward a Chinese letter understanding of the forces that shape reality. To truly appreciate the scale of this cosmic architecture, we have to zoom out from individual galaxies to view the universe in its grandest, most magnificent form. For decades, our best maps of the cosmos revealed something astounding. Galaxies aren't scattered randomly through the void like lonely islands. Instead, they are organized into an immense, web-like structure of unimaginable size and complexity. This is the cosmic web, and it is the largest pattern known to exist. Envision a spider's web spun on a universal scale, with long, delicate filaments of galaxies stretching across billions of light years, connecting at dense, massive nodes where thousands of galaxies swarm together in bustling clusters. Between these brilliant structures lie the cosmic voids, vast deserts of near emptiness that can span hundreds of millions of light years. This breathtaking structure didn't appear fully formed. It grew over billions of years, and for a long time, its origin was a profound mystery. How could a universe that began in an almost perfectly smooth, hot state after the Big Bang evolve into this intricate, clustered tapestry? The answer, according to the Standard Model, lies with dark matter. Its unique properties make it the perfect cosmic architect, because dark matter doesn't interact with light or with itself through electromagnetic forces. It doesn't feel pressure or friction. It is immune to the forces that cause ordinary gas to heat up, radiate energy, and collapse in complex ways. This means dark matter can start clumping together under its own gravity almost immediately after the Big Bang, long before ordinary matter could get its act together. Supercomputer simulations of this process are nothing short of magical. They show how tiny, random quantum fluctuations in the early universe were magnified by inflation, creating minuscule seeds of slightly higher density. Dark matter, responding only to gravity, began to gravitate toward these seeds. As it collapsed, it formed halos, gravitational wells of increasing depth. These wells acted as a scaffold, a hidden framework upon which the visible universe could later assemble. Ordinary matter, in the form of hydrogen and helium gas, eventually felt the irresistible pull of these growing dark matter potentials. It flowed along the invisible filaments of the web, funneling into the halos where it could cool, condense, and finally ignite into the first stars and galaxies. In this story, dark matter is the unseen director, choreographing the entire formation of the cosmic web, while ordinary matter is merely the actor, following its gravitational cues to light up the stage. This model has enjoyed spectacular success. It accurately predicts the statistical distribution of galaxies mapped by monumental projects like the Sloan Digital Sky Survey, which has painstakingly charted the positions of millions of galaxies. The simulated universe generated by dark matter physics looks, on a statistical level, almost identical to the real one we observe. It is a triumphant achievement of modern cosmology. However, every new window we open onto the universe has the potential to reveal surprises that challenge our most cherished models. The James Webb Space Telescope is such a window, and it is already giving us a sharper, deeper view of the infant universe than we have ever had before. Its first glimpses of the cosmic dawn have been simultaneously exhilarating and deeply perplexing. Astronomers are discovering that the early universe was far more structured and evolved than anyone predicted. They are finding fully formed massive galaxies and dazzling black holes at a time when, according to the standard dark matter timeline, the cosmos should have been only taking its first tentative steps toward structure. These galaxies appear too big too soon. They seem to have assembled their immense collections of stars at a breakneck pace that strains the conventional model of gradual growth guided by dark matter's slow, steady gravitational pull. This creates a fascinating tension at the heart of cosmology. The model works flawlessly for the universe's adulthood, accurately describing the cosmic web we see around us today. But it appears to struggle to explain the universe's surprisingly rapid childhood development. If dark matter is the sole architect, why did construction proceed so much faster in the early universe than our blueprints predicted? This discrepancy isn't necessarily a death knell for dark matter, but it is a loud and clear signal that our understanding of structure formation is incomplete. It forces us to consider whether the properties of dark matter might be more complex than the simple, cold, and collisionless picture we've held for so long. Perhaps dark matter particles can interact with each other through some unknown force, transferring energy and speeding up the collapse of early halos. Or maybe there are other, more exotic processes at work in the extreme environments of the young cosmos. This challenge also breathes new life into alternative ideas. Could modified gravity, which so elegantly explains galaxy rotations, also play a role on these vast scales? If the force of gravity is inherently stronger in the low-density environments that dominated the early universe, it could potentially accelerate the collapse of the first structures without needing to tweak the dark matter recipe. The early data from James Webb is not yet conclusive, but it has undoubtedly thrown open the doors to a new era of questioning. It reminds us that the universe's greatest mysteries are often hidden not in what we can easily see, but in the subtle tensions between our most successful theories and the next generation of unexpected observations. This decades-long quest for a direct detection has unfolded like a grand, high-stakes treasure hunt, with physicists building increasingly sophisticated traps in the most silent environments on Earth. To shield their experiments from the constant barrage of cosmic rays and background radiation that would drown out any faint signal, they've gone deep underground. Laboratories housed in abandoned gold mines in South Dakota, beneath mountains in Italy, and in deep tunnels in Canada have become the front line in this search. Inside these subterranean fortresses of science, researchers have built some of the most sensitive detectors ever conceived. At the heart of these experiments are massive vats of ultra-pure liquid xenon or germanium, cooled to extreme temperatures and watched over by arrays of powerful sensors. The principle is straightforward yet brilliant. If a dark matter particle, such as a WIMP, were to drift through the tank and ever so rarely bump into the nucleus of a xenon atom, it would create a tiny flash of light and a minute charge of electricity. These dual signals would be the unmistakable fingerprint of a collision with something from the dark sector. For years, the strategy was to build bigger and bigger detectors, increasing the target size to improve the odds of catching one of these incredibly elusive particles. Projects like LUX, the Large Underground Xenon Experiment, and its massive successor, Lux Zeppelin, along with the Xenon collaboration in Italy, represent the pinnacle of this engineering marvel. Yet, after countless years of operation and analysis, the result has been a profound and puzzling silence. The detectors have remained stubbornly dark, registering no confirmed signal that can be attributed to dark matter. This isn't to say they've found nothing. These experiments are so sensitive they can detect the faint recoil from a neutrino, a nearly massless particle that was itself once a ghostly theoretical concept. They have magnificently confirmed the limits of the standard model of particle physics, but the primary target remains at large. The only consistent claim of a detection comes from the Dama/Libra experiment, also located deep under an Italian mountain, which has reported an annual modulation signal, a tiny, rhythmic rise and fall in detected events for over 2 decades. This pattern, they argue, could be caused by Earth moving through a halo of dark matter particles as it orbits the Sun, creating a slight wind that changes with the seasons. However, no other experiment in the world has been able to reproduce this result, and most in the community remain deeply skeptical, as the signal could potentially be explained by seasonal variations in background radiation or other systemic effects. This relentless null result is far from a failure. In science, a non-detection is still critical data. It has systematically ruled out vast swaths of potential parameter space, effectively telling us what dark matter is not. We now know with great certainty that if WIMP exist, they must be heavier or interact even more weakly than our most conservative models had predicted. They are being pushed into a narrower and narrower theoretical corner. This ever-tightening constraints have created a growing sense of unease, a creeping realization that the most popular and well-motivated candidate for dark matter might be a phantom. The elegant simplicity of the WIMP, once hailed as a prime example of naturalness in physics, is now facing an existential crisis. How long can a community continue to search for something that has evaded every trap set for it, despite those traps becoming exponentially more sensitive? This experimental impasse is forcing a profound and necessary introspection within physics. It is pushing the brightest minds to consider possibilities that were once relegated to the fringe. Perhaps dark matter is not a single, simple particle, but a spectrum of particles with complex interactions, a whole dark sector with its own forces and physics parallel to our own. Maybe it's not a particle at all, but a primordial black hole formed in the first instance after the Big Bang. Or perhaps it's something even more exotic, like action's ultra-lightweight particles born out of theories attempting to solve other deep problems in quantum physics. The continued silence from underground is ironically becoming louder than any detection could be, shouting that our assumptions need a fundamental rethink. It is this very frustration, this decades-long puzzle with missing pieces, that clears the deck for the most radical idea of all, that we need to stop inventing new kinds of matter and start reimagining the very force that holds the cosmos together. This brings us to the most radical frontier of all, a place where the very concepts of space, time, and gravity are being completely reimagined. What if the puzzle of dark matter isn't a call to find a new particle, but a signal that our understanding of the most familiar force in the universe is fundamentally flawed at its core? This isn't about a simple modification like MOND. It's a proposal so profound it suggests that gravity itself might not be what we think it is. For centuries, we've treated gravity as a fundamental force, an innate property of mass that warps the fabric of spacetime. But this view creates an intractable problem when we try to marry it with the quantum mechanics that so perfectly describes the other three forces of nature. The mathematics simply break down, creating infinities and paradoxes that have resisted solution for 100 years. This stalemate has led a growing number of theoretical physicists to consider a breathtaking possibility. Perhaps gravity isn't fundamental at all. In frameworks known as emergent gravity or entropic gravity, the force we experience is not a primary building block of the universe but a secondary effect, a kind of statistical illusion. The most famous of these proposals comes from physicist Eric Verland, who suggests that gravity emerges from the behavior of microscopic degrees of freedom, the fundamental bits of information that make up spacetime itself. Think of it like temperature. We feel temperature as a real, tangible property, but it doesn't exist as a fundamental force. It emerges from the frantic, microscopic jiggling of countless molecules. In the same way, Verland argues gravity could emerge from the changing entropic or informational states of the underlying structure of the cosmos. This perspective completely reframes the dark matter problem. In this view, the anomalous rotations of galaxies and the gravitational lensing we observe aren't caused by the pull of invisible matter. Instead, they are the result of a subtle change in how gravity behaves in environments where the density of visible matter is very low, like the outskirts of galaxies. The equations of entropic gravity naturally produce an extra gravitational effect in these regions, an effect that exactly mimics the presence of dark matter without requiring a single new particle. The mysterious halo is replaced by a new law of physics, one that ties gravity directly to the distribution of information and energy in the universe. It's a stunningly elegant and economical idea, solving two of physics' greatest problems, unifying gravity with quantum mechanics and explaining dark matter with a single conceptual leap. The implications of this are quite literally universe-altering. It suggests that spacetime itself is not a static stage upon which the drama of physics plays out, but a dynamic, emergent property, almost like a fluid that condenses out of a more fundamental reality. This opens the door to even more revolutionary concepts, like the holographic principle, which posits that all the information contained within a volume of space can be encoded on its boundary, a lower dimensional surface. While these ideas are currently highly speculative and mathematically formidable, they are gaining traction precisely because they offer a path forward where others have failed. They represent the ultimate paradigm shift. Instead of adding more and more invisible stuff to our cosmic inventory to fix our equations, we are being forced to reconsider the inventory itself. We might not be missing a type of matter. We might be missing a deeper understanding of the stage on which all matter performs. Among the most fascinating and creative solutions to the dark matter puzzle is the idea that we don't need to invent a new particle at all. Perhaps the answer has been hiding in the most extreme objects we already know exist, black holes. But not the kind born from the dramatic deaths of massive stars. This theory points to something far more ancient and elusive: primordial black holes. Imagine the universe in its very first moments, a seething, dense, and turbulent soup of energy. Within that chaos, theorists propose, tiny regions could have become so incredibly dense that they collapsed directly into black holes, some perhaps no heavier than an asteroid yet as small as a single atom. These hypothetical objects wouldn't need a star to form. They are fossils from the birth of the cosmos itself. If they exist in vast numbers, these primordial black holes could be the perfect candidate for dark matter. They are, by their very nature, completely dark, emitting no light. They have mass and therefore exert a powerful gravitational pull. A galaxy could be filled with a vast swarm of them, a halo of these ancient gravitational anchors, perfectly explaining the rotation curves and the lensing effects without a single WIMP or action. The beauty of this idea is its simplicity. It uses the known laws of gravity and known, albeit extreme, astrophysical objects to solve the mystery. This theory received a significant boost from an unexpected source, the Laser Interferometer Gravitational Wave Observatory, or LIGO. When LIGO began detecting ripples in spacetime from colliding black holes, astronomers were surprised by the masses of the objects involved. Many were in a range of 20 to 40 times the mass of our Sun, heavier than the black holes typically formed from stellar collapse. This odd mass distribution opened the door to a tantalizing possibility. Perhaps LIGO wasn't seeing the end of stellar lives, but the ancient dance of primordial black holes that have been circling each other for billions of years, finally merging and sending their gravitational announcement across the universe. However, like all good theories, this one faces stringent constraints from other observations. If the universe were teeming with enough asteroid mass black holes to account for all dark matter, they would act like tiny lenses, briefly magnifying the light of distant stars as they passed in front of them. Extensive microlensing surveys, like those conducted by the Subaru telescope and others, have diligently searched for these telltale flashes. While they've found a few candidates, there simply aren't enough to suggest that small primordial black holes make up the bulk of dark matter. Similarly, data from the cosmic microwave background places strict limits on larger primordial black holes. If too many existed, their voracious gravitational appetites and their evaporation through Hawking radiation would have left an observable imprint on the delicate thermal radiation from the early universe, an imprint we simply do not see. Yet the story isn't over. The constraints are not absolute, they simply rule out certain size ranges. A population of primordial black holes that are either very small or very large could potentially slip through these observational nets. Some theorists are now exploring the possibility that dark matter could be a mix of different substances, perhaps a population of primordial black holes in a specific mass window, combined with another type of particle. This illustrates the remarkable creativity and resilience of cosmology. When one door closes, scientists don't abandon the search. They instead look for a slightly ajar window, exploring every conceivable nook and cranny of possibility. The ongoing investigation into primordial black holes is a perfect example of this, showing that even in the face of daunting evidence, the most compelling ideas find a way to adapt and evolve. While we've been focusing on the gravitational glue holding galaxies together, an even more powerful and enigmatic force is at work on the grandest stage of all, relentlessly stretching the very fabric of the cosmos. This is dark energy, and its discovery at the end of the 20th century was arguably the most shocking cosmological revelation since the realization that the universe was expanding in the first place. For decades, astronomers had assumed that the universe's expansion, set in motion by the Big Bang, must be gradually slowing down over time due to the collective gravitational pull of all the matter within it. The only question was whether that slowdown would eventually lead to a big crunch or simply coast toward a gradual halt. Two teams set out to measure this deceleration by observing distant supernovae, using these stellar explosions as standard candles to gauge the expansion rate of the universe across billions of years. To their absolute astonishment, they found the opposite. The expansion wasn't slowing down at all, it was speeding up. The universe was accelerating outward, as if some repulsive force, stronger than gravity itself, was blowing the cosmos apart from within. This discovery, which earned the Nobel Prize in Physics in 2011, forced us to acknowledge that ordinary matter and even dark matter together make up less than a third of the universe's total content. The dominant component, a staggering 68%, is this mysterious dark energy. This revelation adds a profound new layer of complexity to our dark matter puzzle. We are now grappling with not one, but two invisible, dominant components of the universe that we fundamentally do not understand. One, dark matter, acts as a cosmic attractor, pulling structures together through gravity. The other, dark energy, acts as a cosmic repulsor, pushing space itself apart. For a long time, these were treated as separate problems with separate solutions. But what if that's the very mistake that has been holding us back? What if dark matter and dark energy are not two independent mysteries, but are in fact two different faces of the same, deeper, and utterly unknown phenomenon? This radical idea is at the heart of theories proposing a unified dark fluid, sometimes poetically called quintessence. In these models, a single substance permeates all of space, and its properties evolve and change over the lifetime of the universe. In the dense, early cosmos, this fluid behaved like cold, dark matter, clumping together under gravity to provide the scaffolding for galaxies. But as the universe expanded and became more diffuse, the nature of this fluid transformed. It began to exhibit a negative pressure, generating the repulsive effect we now call dark energy. In this view, the two great unknowns of cosmology are simply different phases or manifestations of a single underlying entity, a chameleon-like substance that adapts to the conditions around it. The appeal of such a model is its breathtaking elegance and economy. Instead of inventing two separate, unrelated components to explain two different sets of observations, it offers a unified solution. It could potentially explain why the densities of dark matter and dark energy are of the same order of magnitude in our current epoch, a curious coincidence that the standard model simply accepts. Perhaps we don't live in a special time. Perhaps we are witnessing the tail end of a seamless transition, where the dark matter that built the structures is now fading into the dark energy that will ultimately determine their fate. This isn't just about simplifying the cosmic inventory. It's about seeking a more fundamental law that governs the behavior of the vacuum of space itself. However, this conceptual beauty comes with immense challenges. Constructing a mathematical model for such a fluid that can simultaneously explain the detailed rotation of individual galaxies, the growth of the cosmic web, and the accelerated expansion of the entire universe is a formidable task. Many proposed models struggle to match all the observational data as precisely as the separate dark matter and dark energy paradigm can. Furthermore, like the particle hypothesis, these unified models currently lack any direct smoking gun evidence. They remain brilliant and compelling thought experiments that highlight the limitations of our current thinking. This push toward unification, whether it ultimately proves correct or not, represents a crucial shift in the philosophy of cosmology. It reminds us that the universe is a single, interconnected system, and that solving its greatest puzzles requires a holistic approach. We can no longer afford to study galaxy rotations in isolation from the expansion of the universe. The same fundamental truth must explain why a star stays bound to its galaxy and why that galaxy is rushing away from all others at an ever-increasing speed. The interplay between these two dark components forces us to consider the entire life cycle of the cosmos, from its first moments to its ultimate destiny, pushing our search for answers toward a grander, more complete theory of everything. This remarkable success of the standard cosmological model, known as lambda cold dark matter or lambda CDM, is a testament to decades of brilliant theoretical work. It provides a single, elegant framework that beautifully explains the universe's large-scale structure, from the cosmic microwave background to the vast web of galaxy clusters. But as our observational tools have sharpened, allowing us to peer into the finer details of individual galaxies, a series of persistent and puzzling cracks have begun to appear in this otherwise magnificent edifice. The model, for all its grand-scale triumphs, seems to struggle with the small print, the intricate details of how dark matter behaves within the confines of a single galaxy. These aren't minor quibbles, they are fundamental mismatches between what our most sophisticated computer simulations predict and what we actually see through our telescopes. One of the most stubborn of these issues is known as the Core-Cusp Problem. According to the lambda-CDM model, dark matter is cold and collisionless, meaning these particles should swarm toward the centers of galaxies, piling up into an incredibly dense, sharp peak, a cusp, at the very heart of every dark matter halo. This is what the physics of gravitational collapse demands for a substance that feels no pressure and doesn't interact with itself. However, when astronomers measure the distribution of dark matter in real dwarf galaxies by charting the motions of their stars, they consistently find something very different. Instead of a steep, dense cusp, they discover a much gentler distribution, a constant density core where the dark matter seems to have been smoothed out, as if someone has stirred it. It's the difference between a perfectly sharpened pencil tip and a rounded, worn-down eraser. This discrepancy is not just a minor accounting error. It suggests that our basic assumption about dark matter being entirely non-interacting might be wrong. If these particles truly never bump into each other, why don't they form those predicted dense central cusps? Then there is the curiously named missing satellites problem. Our breathtakingly detailed simulations of cosmic structure formation, which use lambda-CDM as their rulebook, produce a universe that is teeming with small-scale structure. They predict that our own Milky Way galaxy should be surrounded by a vast swarm of hundreds, even thousands, of small dwarf galaxy satellites, each held in its own tiny dark matter halo. But when we go out and actually count them, we find far fewer. Only a few dozen have been confirmed. For a long time, astronomers thought this was simply an observational limitation, that these satellites were too faint for our telescopes to see. But as our instruments have improved, we've discovered more of these faint dwarfs, yet the number still falls dramatically short of the simulated prediction. This forces us to ask a difficult question. Is the problem that our telescopes aren't good enough, or is the problem that our simulation's rulebook is missing a crucial page? Perhaps the dark matter model requires a tweak that suppresses the formation of these smallest structures. A related issue is the challenge of creating realistic disk galaxies like our own Milky Way. In many lambda-CDM simulations, the process of galaxy formation is simply too violent. Large galaxies are built through a relentless series of mergers with smaller ones. While this does indeed happen, these simulated mergers often leave the resulting galaxy too puffed up and disordered, with stars orbiting in every which direction. What we see in reality, however, are beautiful, thin, and relatively calm spiral disks. It's as if the simulations are producing galaxies that have been stirred too vigorously, while nature has a way of keeping things remarkably settled and organized. This too-big-to-fail problem, another famous challenge, notes that the simulated dark matter halos are so massive that they should host galaxies far brighter and larger than the dwarf galaxies we actually observe orbiting our galaxy. The simulations predict giants where we see only faint ghosts. These are not mere failures of coding or processing power. They are glaring signs that our understanding of dark matter's fundamental nature is incomplete. The physics we are programming into these supercomputers, based on the simple, cold, and collisionless description, might be an oversimplification of a much richer reality. This realization has sparked a new wave of theoretical innovation as cosmologists begin to play with the rules of the game. What if dark matter isn't completely cold? The concept of warm dark matter introduces particles that were moving fast enough in the early universe to smooth out some of the smallest scale fluctuations, potentially resolving the missing satellites problem by preventing the very smallest halos from ever forming. Others are exploring the possibility that dark matter might have a little interaction after all. Models of self-interacting dark matter propose that these particles can indeed collide with one another, much like molecules in a gas. This simple change has profound effects. In a galactic center where the density of dark matter is highest, these collisions would transfer energy, effectively scattering particles away from the core and smoothing out the predicted cusp into the observed core. It could also explain why some galaxies appear to have their dark matter stripped away during collisions, while in others it seems to stay put. These are not wild guesses. They are serious, mathematically rigorous attempts to align our theoretical models with the hard data from observations. Each small-scale problem is a precious clue, a fingerprint left by the true nature of dark matter on the cosmos we see. The fact that Lambda Centium, for all its glory, fails to explain these details is not a cause for despair but for excitement. It means the universe is still holding secrets, and we are getting closer to uncovering them. The gaps between simulation and reality are not a sign of failure. They are the very guideposts that are leading us toward a deeper, more nuanced, and ultimately more truthful understanding of the invisible forces that have shaped everything we know. Just when cosmologists thought they were closing in on a coherent model of the universe, a new and even more profound mystery emerged from the data, one that strikes at the very heart of our understanding of cosmic history. This puzzle is known as the Hubble Tension, and it represents a genuine crisis in modern cosmology. The issue is deceptively simple. We have two incredibly precise, yet completely independent, methods for measuring how fast the universe is expanding, and they stubbornly refuse to agree. It's as if you used two different brands of impeccably calibrated rulers to measure the same table and got two different, yet equally confident, answers. This isn't a small margin of error. It's a persistent and statistically significant discrepancy that has only grown more pronounced as our measurements have become more accurate. To understand why this is so troubling, we need to look at these two rulers. The first method peers back to the very infancy of the universe, roughly 400,000 years after the Big Bang. This is when the cosmos cooled enough for light to finally travel freely, creating the cosmic microwave background radiation, that faint afterglow that fills all of space. Exquisitely detailed maps of this radiation, most famously from the Planck satellite, allow us to take a snapshot of the baby universe. By analyzing the tiny fluctuations in temperature and density within this snapshot, and then applying the well-established physics of the standard Lambda Centium model, cosmologists can predict how this infant universe should evolve. They can essentially press fast forward on the simulation and calculate what the expansion rate should be today. This method gives us a very specific value for the Hubble constant, which is the rate of the universe's expansion. The Planck measurement is incredibly precise, but it relies on the assumption that our standard model of cosmology is complete and correct. The second method takes a completely different approach, measuring the expansion rate directly in our own cosmic neighborhood. Astronomers use certain types of supernova explosions and pulsating stars called Cepheid variables as standard candles. Because we know their intrinsic brightness, we can measure how bright they appear from Earth and accurately calculate their distance. By combining these distance measurements with readings of how fast these galaxies are moving away from us, their redshift, we get a direct empirical measurement of the Hubble constant in the present-day universe. This is like measuring the expansion rate in real time without needing to assume any particular cosmological model. Teams using the Hubble Space Telescope and other observatories have refined this local measurement to an astonishing degree of precision. Here is where the crisis erupts. The value from the early universe and the value from the late universe do not match. The local measurements suggest an expansion rate that is significantly faster, about 10% faster, than the rate predicted by the early universe data. This Hubble tension is now confirmed at a confidence level of 5 sigma, which in the world of physics is the gold standard for a genuine discovery, not a fluke. This means there is only a 1 in a million chance that this discrepancy is due to random error. We are therefore faced with an inescapable conclusion: something is fundamentally wrong. Either our measurements of the early universe are somehow flawed in a way we don't understand, or our standard model of cosmology is missing a crucial ingredient. This is where the mystery of dark matter comes roaring back into the picture. The lambda CDM model, which so successfully describes the cosmic web, depends on a very specific recipe: about 5% ordinary matter, 27% cold dark matter, and 68% dark energy. The Hubble tension suggests that this recipe, while good, might not be perfect. Perhaps dark matter is not as simple and cold as we have assumed. Some theorists are exploring the idea of early dark energy, a speculative form of energy that could have briefly surged in the very early universe, altering its initial conditions just enough so that when we fast forward to the present day, the predicted expansion rate aligns with what we actually measure locally. Others are considering whether dark matter might have some unusual properties, perhaps interacting with itself or with dark energy in ways that subtly change how structures form and how the expansion evolves over billions of years. The implications of the Hubble tension are staggering. It is not a minor puzzle to be solved within the existing framework. It is a glaring signpost pointing toward entirely new physics. Resolving it might require us to rethink the nature of dark energy, making it a dynamic force that changes over time rather than a constant cosmological constant. It might force us to reconsider the fundamental properties of dark matter, or even the nature of gravity itself on cosmological scales. Each passing year that the tension remains unresolved adds more weight to the possibility that our current cosmological model, for all its triumphs, is merely a very good approximation of a much stranger and more complex reality. The Hubble tension is the universe's way of telling us that we are on the verge of a revolution, one that will demand a radical rewrite of the cosmic story we thought we knew. But what if the solution to this cosmic standoff isn't about choosing one side over the other, but finding a way to unify them into a single, elegant framework? This is the promise of one of the most fascinating and innovative ideas to emerge in recent years: superfluid dark matter. Imagine a substance that is so bizarre it defies our everyday experience. A superfluid is a unique state of matter that flows with absolutely zero friction or viscosity. In laboratories on Earth, we can create superfluids by cooling certain liquids like helium to temperatures just a fraction of a degree above absolute zero. At these extreme conditions, the fluid can climb up the walls of its container and flow through impossibly tiny cracks without losing any energy. Now, envision this exotic behavior translated to a cosmic scale. Theorists propose that dark matter itself could be a superfluid, condensing into a giant, galaxy-spanning halo that envelops structures like our Milky Way. In the cold, sparse depths of interstellar space, this dark matter superfluid could form naturally. Within this halo, the superfluid wouldn't just sit there passively. It would be buzzing with quantum activity. The constant, tiny vibrations within the fluid, known as phonons, would generate a new, emergent force. This force wouldn't be a fundamental force like gravity, but a collective effect, much like the pressure waves that form in a crowded room full of people talking. This is where the magic happens. On the scale of an individual galaxy, these phonons, these quantum vibrations in the dark matter superfluid, would produce an additional force that perfectly mimics the effects of modified Newtonian dynamics. It would provide that extra gravitational-like kick in the low acceleration outskirts of galaxies, explaining the flat rotation curves without needing to modify Newton's laws themselves. The superfluid's phonons are effectively doing the job of MOND. But when we zoom out to the scale of the entire cosmos, the superfluid behaves just like the cold, collisionless dark matter we've always needed. It clumps together under gravity to form the scaffolding for the cosmic web, and it explains the gravitational lensing we see around massive galaxy clusters. In this single, brilliant model, you get a dual explanation. It acts like MOND where you need it to on galactic scales, and it acts like standard dark matter where you need it to on cosmological scales. This proposal represents a stunning synthesis of two seemingly irreconcilable worlds. It doesn't throw out the dark matter paradigm, it enriches it with new physics. It also doesn't dismiss the incredible predictive success of MOND on galactic scales. It provides a potential physical mechanism for why it works. The superfluid model is still highly speculative and faces its own set of challenges, particularly in working out the precise details of how this superfluid forms and evolves over the history of the universe. But its very existence is a powerful testament to the creative ways physicists are responding to the mounting pressures on traditional models. It shows a willingness to explore the blurry boundary between matter and force, suggesting that the ultimate answer to the dark matter mystery may not be a simple particle, but something far more complex and wondrous, a dynamic quantum entity whose behavior is dictated by the environment it's in, seamlessly shifting its nature to match the scale of the cosmos it helps to shape. While we've been exploring the grand cosmic mysteries of dark matter and modified gravity, it's worth remembering that the universe has already provided us with a perfect example of a real, detectable, yet incredibly elusive particle, the neutrino. These ghostly subatomic entities are produced in abundance by nuclear reactions in stars, supernova, and even here on Earth in particle accelerators and nuclear reactors. Trillions of them are passing through your body every second, completely unnoticed because they barely interact with ordinary matter at all. In many ways, neutrinos are the closest thing we have to a known form of dark matter. They are massive, yet for decades we thought they were massless. They are everywhere, yet they are famously difficult to catch. This naturally led physicists to ask a compelling question. If the universe is already filled with one type of invisible, weakly interacting particle, could neutrinos themselves be the answer to the dark matter enigma? The short answer, based on our current understanding, is no. Standard neutrinos, while fascinating, have a critical flaw that disqualifies them from being the primary constituent of dark matter. They move far too fast. Born from high-energy processes, these particles are relativistic, zipping through the cosmos at a significant fraction of the speed of light. This high velocity gives them a defining characteristic: they are hot. In cosmological terms, hot dark matter doesn't clump together under gravity. Instead, it tends to stream freely, washing out and smoothing over the very small-scale density fluctuations that are the essential seeds for galaxy formation. If dark matter were primarily made of these standard neutrinos, the gravitational wells they formed would be too shallow and too spread out. Galaxies would not have had time to coalesce into the intricate structures we see today. the cosmic web would be a faint, blurry smear rather than the sharp, filamentary network we observe. The universe would look entirely different. However, the story doesn't end there. The world of particle physics is rich with hypothetical possibilities, and one particularly intriguing idea involves a heavier, even more elusive cousin of the neutrino, the sterile neutrino. As the name implies, this hypothetical particle would be sterile because it wouldn't interact through any of the fundamental forces of the standard model of particle physics. Not the weak force, not the electromagnetic force, nothing. Its only connection to our familiar world would be through gravity and, potentially, through occasional oscillations with the standard neutrino types we already know. This sterility would make it a perfect candidate for cold dark matter. If sterile neutrinos have the right mass, they would be slow-moving enough to clump together gravitationally, providing the scaffolding for galaxies without streaming away and blurring the cosmic landscape. The appeal of sterile neutrinos extends beyond just theory. They have been proposed as a potential solution to several lingering anomalies in both particle physics and astronomy. For instance, unexpected results from certain neutrino detection experiments have shown curious bumps or excesses in data that could, some physicists argue, be interpreted as a hint of a fourth, sterile neutrino type. Furthermore, in the astronomical realm, sterile neutrinos could potentially explain the puzzling overabundance of intense X-ray emission detected from certain galaxy clusters. If sterile neutrinos were to decay, a theoretical possibility, they could produce a photon at a very specific energy, creating a faint monochromatic glow that might be detectable. Some astronomers believe they have spotted a tantalizing, unexplained X-ray line at an energy of 3.5 kilo-electronvolts that could be this very signature, though the evidence remains controversial and far from confirmed. This ongoing hunt for sterile neutrinos exemplifies the dynamic interplay between the incredibly large and the unimaginably small in modern cosmology. Massive detectors like the upcoming Deep Underground Neutrino experiment are designed to probe the properties of neutrinos with unprecedented precision, and part of their mission is to search for any subtle deviations that might point toward the existence of these sterile partners. Finding them would be a monumental achievement, seamlessly weaving a new particle into the existing fabric of the standard model, while simultaneously providing a compelling component for the dark matter that shapes the cosmos. It would be a beautiful unification of particle physics and cosmology, even if sterile neutrinos are never found, or if they turn out to contribute only a small fraction of the total dark matter budget. Their investigation is far from a wasted effort. The continued study of all neutrinos serves as a crucial reminder. It shows us that the universe is already teeming with particles that defy our everyday experience, entities that are massive yet barely there. This reality opens the door to the possibility that dark matter isn't a single, monolithic substance. Instead, the missing mass of the universe could be a diverse population, a cosmic zoo of different exotic particles, each with its own unique properties and behaviors. Sterile neutrinos might be one resident of that zoo, alongside WIMP actions or other entities we have not yet even dreamed of. This perspective encourages a broader, more flexible approach to one of science's greatest puzzles, reminding us that the final answer may be more complex and more wonderful than any single theory can contain. While we often picture the vast expanses between galaxies as perfect, empty voids, they are in fact threaded with invisible forces of their own. Among the most subtle yet widespread of these are intergalactic magnetic fields. These are not the powerful, concentrated magnets we know on Earth, but incredibly faint, diffuse fields that stretch for millions of light years, weaving through galaxy clusters and the cosmic web itself. Their origins are still debated, perhaps seeded by ancient quasars or amplified by the turbulent motions of primordial plasma in the early universe. Though their strength is minuscule, often billions of times weaker than Earth's magnetic field, their sheer scale means they could exert an influence we are only beginning to appreciate. The conventional view has long held that gravity is the sole architect of cosmic structure, with magnetism playing a secondary role. But as our simulations and observations improve, that assumption is being challenged. Consider the behavior of charged particles, which are abundant in space in the form of free electrons and ions. As these particles travel through these vast magnetic fields, their paths are curved and guided, a process that can transfer energy and momentum throughout a galaxy or a cluster. In certain regions, particularly in the hot, ionized gas that surrounds galaxies and fills clusters, the pressure exerted by these magnetic fields could become significant. This magnetic pressure might subtly alter the motion of this gas, which in turn could influence how we interpret the gravitational forces at play. This leads to a fascinating, though speculative, possibility. Could these large-scale magnetic fields, through their effect on ionized gas, create forces that mimic the gravitational pull we attribute to dark matter? In areas where the gas is dense and the magnetic fields are unusually strong, the additional pressure might provide just enough extra force to explain why some galactic disks rotate faster than expected, or why certain structures appear more bound than their visible mass would allow. It's a compelling thought experiment that asks whether we've been misinterpreting an electromagnetic effect for a gravitational one. It's crucial to emphasize that this idea remains a minority viewpoint within cosmology. The forces required to fully account for the dark matter phenomenon are immense, and it is difficult to see how magnetic fields alone, given their observed weakness, could provide the complete answer. However, the value of this line of inquiry isn't necessarily in replacing dark matter, but in highlighting the beautiful complexity of the cosmos. It reminds us that our models, however sophisticated, are simplifications. We may be overlooking a symphony of subtle interactions between known forces, where electromagnetism and gravity perform an intricate dance on a cosmic stage. This underscores a much larger point in our quest to understand the universe's hidden workings. The true answer may not be a simple choice between dark matter and modified gravity, but a more nuanced picture that incorporates a variety of overlooked phenomena. Intergalactic magnetic fields represent one such piece of a larger puzzle, a reminder that the universe is governed by a rich interplay of forces we are still learning to measure. As we develop new tools to map these faint magnetic signatures across the void, we may find that they contribute a crucial verse to the cosmic story, helping to explain certain anomalies and adding another layer of depth to our understanding of the unseen architecture of everything. And now, the James Webb Space Telescope has thrown a brilliant, dazzling wrench into the works, presenting us with a universe that seems to have grown up far too fast. This extraordinary observatory, peering deeper into space and further back in time than any telescope before it, was designed to see the cosmic dawn, the very first stars and galaxies flickering to life. Instead of finding a universe taking its first tentative steps, JWST has revealed a cosmic toddler that's already running. It's like opening a family photo album expecting to see pictures of a newborn, only to discover full-page portraits of a teenager. The specific puzzle lies in the size and maturity of these incredibly ancient galaxies. The standard model of cosmology, our trusted lambda CDM, provides a detailed timeline. After the Big Bang, the universe needed time to cool. Then, dark matter had to gradually clump together under its own gravity, forming those invisible halos that would later act as gravitational wells. Only then could ordinary matter, the hydrogen and helium gas, flow into these wells, cool down, and eventually condense to ignite the first stars. This process was predicted to be a slow, gradual build-up, taking hundreds of millions of years. The very first galaxies, we thought, would be small, fragile, and relatively simple. JWST powerful infrared eyes have shown us that this story of gradual growth might be a dramatic understatement. The telescope has discovered galaxies that existed when the universe was a mere 3 to 5% of its current age, a time so early it was once thought to be a dark, formless epoch. But these aren't just faint, primordial specks. They are massive, fully formed systems, brimming with stars and heavy elements that should only have been forged over many generations of stellar life and death. They appear polished, mature, and astonishingly massive, having assembled an immense amount of material at a pace that seems to defy the gradualist predictions of the dark matter model. It's the equivalent of finding a majestic, ancient oak tree in a forest we just planted last week. This creates a fascinating and profound tension for cosmologists. If these galaxies are as massive and as evolved as they appear, it means the entire process of structure formation had to have been jump-started somehow. The dark matter scaffolding must have assembled with breathtaking speed. This forces a serious reconsideration of dark matter's fundamental properties. Perhaps it isn't as perfectly cold and non-interacting as we've assumed for decades. Maybe dark matter particles can interact with each other through some unknown force, allowing them to shed energy and collapse into halos much more efficiently and rapidly than our models allow. This self-interacting dark matter could potentially solve this puzzle of precocious galactic growth, while also addressing some of the smaller-scale problems we see in modern galaxies. Another possibility is that our understanding of the very first stars is incomplete. Perhaps the earliest generations of stars were unimaginably gigantic, burning furiously bright and dying in spectacular supernova that enriched the cosmos with heavy elements at a ferocious rate, seeding the rapid growth of the next generation of stars and galaxies. Or maybe there were other, more exotic mechanisms at play in the incredibly dense early universe that funneled gas into forming galaxies with an efficiency we simply haven't accounted for in our simulations. Each stunning image from JWST is more than just a beautiful postcard from the edge of time. It is a data point that challenges our most fundamental assumptions. The telescope isn't just showing us what's out there, it's holding up a mirror to our theories and revealing where they might be cracked. These observations of an unexpectedly mature infant universe don't necessarily destroy the lambda CDM model, but they are a powerful warning that our picture is incomplete. They urge us to think outside the box, to consider that the dark universe might be far more dynamic and complex than a simple sea of inert particles. Every galaxy that looks too big too soon is a direct challenge, a cosmic provocation that is forcing a new and thrilling chapter in our quest to understand the invisible forces that built everything we see. This concept invites us to perform a profound shift in perspective, to consider that the answer to the dark matter mystery might not be found by inventing a new substance, but by listening more carefully to the faint, quantum hum of empty space itself. According to quantum field theory, the vacuum is not a barren, static nothingness. It is a seething, bubbling sea of potentiality, alive with transient phenomena known as virtual particles. These particle-antiparticle pairs constantly flicker into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and returning it. This isn't just a mathematical quirk, it's a fundamental property of reality with measurable consequences, like the Casimir effect, where two uncharged metal plates placed incredibly close together in a vacuum are gently pushed together by the pressure of these quantum fluctuations outside them. This vacuum energy, sometimes called zero-point energy, is immense. In fact, when theorists first tried to calculate its total value, the result was an absurd number, an energy density so catastrophically large that it would have caused the universe to expand so rapidly that not even atoms could have formed. This staggering miscalculation, off by a factor of 1 followed by 120 zeros, is known as the cosmological constant problem and stands as one of the greatest embarrassments in theoretical physics. It clearly shows that our understanding of the quantum vacuum and its interaction with gravity is woefully incomplete, but within that profound ignorance may lie the seeds of a solution. Some of the most innovative theoretical work today explores how this vibrant vacuum might interact with gravity in ways we haven't yet imagined. The equations of general relativity are incredibly powerful, but they were forged in a classical world before the bizarre rules of quantum mechanics were fully understood. It is entirely possible that when we finally achieve a theory of quantum gravity, new terms will appear in Einstein's equations, terms that describe how the vacuum's energy content curves spacetime. Under certain conditions, particularly in the low-density, vast environments of galactic halos and intergalactic space, these new terms could produce an additional gravitational effect. This effect wouldn't come from clumps of invisible matter, but from the inherent energy of space itself, and it could perfectly mimic the presence of dark matter, explaining the rotation curves of galaxies and the lensing around clusters. This approach is beautifully economical. It doesn't require populating the universe with a whole new class of undetectable particles. It simply suggests we need a deeper, more complete theory of how the things we already know exist. The quantum vacuum and spacetime interact with one another. The focus shifts from a hunt for a hidden substance to a quest for a hidden relationship, a more fundamental law that unifies the quantum world with the gravitational cosmos. The mysterious dark matter halo surrounding a galaxy could be reinterpreted not as a cloud of particles, but as a region where the modified properties of the quantum vacuum generate a stronger gravitational field than our current theories predict. In this view, dark matter is an illusion, a placeholder for our ignorance of how gravity truly behaves in the quantum realm. While these ideas remain highly speculative and far from a tested theory, they represent a thrilling direction for fundamental physics, one that could ultimately solve two mysteries: dark matter and the nature of quantum gravity, with a single, elegant stroke. These profound questions lead us to a deeply philosophical crossroads, a concept that forces us to confront not just the mechanics of the cosmos, but the very reason we are here to observe it. This is the realm of the anthropic principle, a fascinating and sometimes controversial line of reasoning which suggests that the universe's fundamental constants and laws must be compatible with the existence of conscious observers. In simpler terms, the universe we see is the way it is because if it were any different, we wouldn't be around to see it. When we apply this lens to the dark matter debate, it opens up a startling new dimension to the mystery. For decades, the standard argument has been that dark matter isn't just a convenient explanation, it's a necessary one for our own existence. The narrative is compelling. In a universe dominated only by the visible matter we see, gravity would have been far too weak to efficiently pull things together after the Big Bang. The primordial gas would have simply drifted apart, never collapsing into the dense clouds needed to ignite the first stars. Galaxies as we know them would never have formed. There would be no planets, no stable solar systems, and certainly no life. Dark matter, in this view, is the unseen hero of our cosmic story. Its immense gravitational pull provided the essential scaffolding, accelerating the formation of structures and creating the galaxies that would eventually become cradles for life. From this perspective, the fact that we find ourselves in a universe rich with dark matter isn't a coincidence. It's a prerequisite for our very ability to ponder it. This anthropic argument has been a powerful pillar supporting the dark matter paradigm. It paints a picture of a unique, life-friendly cosmos whose recipe absolutely requires this invisible ingredient. But what happens to this argument if alternative theories like modified Newtonian dynamics can also successfully explain the formation of galaxies and large-scale structures? The foundation suddenly weakens. If a universe without dark matter particles could still, through a modification of the laws of physics, create the galaxies necessary for life, then dark matter is no longer a unique necessity. It becomes merely one possible way, among others, that a universe could configure itself to be habitable. This doesn't disprove dark matter, but it dramatically shifts the philosophical weight. It suggests that the conditions for life might be achievable through multiple cosmic pathways, and our universe may have simply taken one particular road. This broader perspective forces a moment of profound humility. It encourages us to ask whether our strong attachment to the dark matter solution is influenced by an unconscious bias, a preference for a narrative where our existence is tied to a specific, dominant component of the cosmos. Are we, as observers, inadvertently favoring theories that place us at the center of a grand, life-dependent scheme? The anthropic principle, when applied carelessly, can be used to justify almost any observed state of the universe by simply stating, "It had to be this way for us to be here." This can potentially stifle curiosity and close off more creative explanations. The real value of this principle is not in providing easy answers, but in asking better questions. It challenges us to disentangle what is truly necessary for life from what is merely a contingent feature of our particular cosmic neighborhood. Ultimately, this philosophical angle expands the conversation far beyond astrophysics and into the realms of metaphysics and probability. It invites us to consider our place in a potentially vast multiverse, a cosmic landscape where countless universes may exist with different physical laws. In such a scenario, we naturally find ourselves in one of the rare universes whose laws, whether they include dark matter or a modified form of gravity, allow for galaxies and life to emerge. This doesn't make the quest to determine our universe's true nature any less urgent. It makes it more so. We are not just mapping the heavens, we are reading the unique signature of our own cosmic home, deciphering whether its story is one of a singular, invisible substance or a deeper, more nuanced set of physical laws. The answer will tell us not only what holds the galaxies together, but what kind of universe we have the privilege to inhabit. Perhaps the most imaginative and truly speculative frontier in this entire discussion lies not in the realm of physics, but in the domain of possibility, the chance, however faint, that the dark matter enigma is not a natural phenomenon at all, but a technological one. This line of thinking ventures into the search for technosignatures, potential signs of advanced civilizations whose activities might be detectable across interstellar distances. The idea is not that dark matter itself is alien, but that a sufficiently advanced culture might have learned to manipulate it. Imagine a civilization that has mastered the universe not just by using stars and planets, but by engineering the very fabric of its unseen components. If dark matter makes up the majority of matter, a Type 2 or Type 3 civilization on the Kardashev scale might see it not as a mystery, but as the ultimate energy source or the foundation for technology operating on a galactic scale. Their artifacts or power generation systems could, in theory, be hidden within those vast halos, completely invisible to our telescopes but detectable through their gravitational signature. Now, it is absolutely vital to state clearly that there is not a single shred of empirical evidence to support this idea. It resides firmly in the category of exciting science fiction rather than established science. Most serious cosmologists would rightly consider it an extreme long shot, a hypothesis of last resort when all other natural explanations have been exhausted. And yet, the value of such a wild speculation isn't in its likelihood, but in its power to jolt us out of our intellectual complacency. For centuries, our understanding of the cosmos has been repeatedly upended by discoveries that were once considered heretical or absurd. The notion that the Earth revolved around the Sun, that continents could drift, or that space itself could be curved, were all once radical thoughts that shattered existing paradigms. Contemplating a connection between dark matter and advanced intelligence is a modern-day exercise in that same radical humility. It forces us to acknowledge that our current scientific models, however successful, are built on a foundation of what we currently know to be possible. The universe, in its 13.8 billion-year history, might hold processes and phenomena that simply lie outside our current conception of reality. This is where the more serious, grounded pursuit of technosignature research comes in. While not hunting for dark matter aliens, projects like the search for Dyson spheres, anomalous laser emissions, or strangely structured planetary systems are all efforts to apply rigorous scientific methodology to the question of whether we are alone. This entire endeavor is built on the premise that other intelligences might not communicate in ways we expect, but they would still have to obey the laws of physics, and in doing so, might leave an imprint on their environment that we could detect. The persistent mystery of dark matter serves as a constant reminder that our map of those physical laws is still incomplete. There could be entire chapters on energy, gravity, and matter that we haven't yet written, chapters that another civilization might have already mastered and applied. The greatest surprise awaiting us may not be a specific particle in a detector, but the staggering realization that the cosmic darkness we've been trying to illuminate is not empty at all. It's full of wonders and technologies so advanced they are indistinguishable from the natural workings of the universe itself. This perspective doesn't provide answers, but it powerfully reinforces the most important principle in all of science: the need to remain open, curious, and utterly astonished by the possibilities that lie hidden in the unknown. But what if the very laws we're struggling to understand aren't universal laws at all, but merely local ordinances? This is the breathtaking premise of the multiverse hypothesis, a concept that radically reframes our search for dark matter not as a quest for a fundamental truth, but as a study of a cosmic accident. Imagine an infinite ocean of reality where each bubble is a self-contained universe, each with its own unique set of physical constants and fundamental forces. In some of these universes, the strength of gravity might be 1,000 times stronger, causing matter to collapse into black holes almost instantly. In others, the weak nuclear force might be so feeble that stars could never ignite. And in this vast, teeming landscape of possibilities, the specific properties of our universe, including the exact amount and behavior of dark matter, begin to look less like a necessary foundation and more like a random roll of the cosmic dice. Within this framework, dark matter transforms from a universal constant into a variable. Some universes might be utterly devoid of it, composed only of the ordinary matter we can see. In such a place, gravity would be too weak to form any large-scale structures at all. Galaxies would never coalesce, and the cosmos would remain a forever dark and formless haze of hydrogen and helium. Other universes might be absolutely dominated by dark matter, with ratios far exceeding our 27%. There, the gravitational pull would be so overwhelming that it might crush all ordinary matter into bizarre, ultra-dense forms, preventing the delicate chemistry required for life as we know it. Our own universe seems to occupy a curious and seemingly precarious golden mean, with just enough dark matter to efficiently sculpt magnificent galaxies and galaxy clusters, yet not so much that it prevents those galaxies from giving birth to stars and planets. This perspective doesn't solve the dark matter puzzle, but it profoundly changes how we might approach it. It encourages physicists to build models where dark matter is not a fixed, immutable entity, but a parameter that can vary. Instead of asking, what is dark matter, we might also ask, why does our universe have this particular kind of dark matter? This line of thinking is a modern incarnation of the Copernican revolution, which gradually moved Earth from the center of the universe to just another planet orbiting an average star. Now we are being asked to consider that our entire cosmos, with all its specific laws and constants, might itself be average, just one possibility in an unimaginably vast ensemble of realities. The properties of dark matter, which seem so essential and non-negotiable to us, might be entirely different next door in a cosmological sense. Of course, the most significant criticism of the multiverse idea is its current untestability. By definition, these other universes would be causally disconnected from our own, placing them firmly outside the realm of direct empirical investigation. For many scientists, this is a fatal flaw, reducing the hypothesis to a philosophical speculation rather than a scientific theory. Yet, even in its untestable form, it serves a powerful purpose as a conceptual tool. It acts as a constant reminder against intellectual arrogance, cautioning us that the solutions we find for our universe may not be the only ones possible. It pushes theorists to be more creative, to consider a wider range of models for dark matter, because the ultimate answer might not be a single particle, but a spectrum of possibilities across the multiverse. While we may never directly observe another universe, the very act of contemplating their existence expands our imagination, freeing us to consider that the dark matter holding our galaxies together is not the final word on reality, but simply our local version of a much grander and more mysterious cosmic story. After decades of theorizing and searching, we are now entering an era where technology is finally catching up to our ambition, launching a multi-pronged assault on the dark matter enigma that is more sophisticated and determined than anything that has come before. This isn't a single experiment or a lone telescope. It's a coordinated campaign happening deep underground in the freezing void of space and at remote mountaintop observatories, each effort designed to probe a different facet of the mystery. The goal is no longer just to find a single particle, but to comprehensively test the entire framework of our understanding, leaving no theoretical stone unturned. Soaring above the distortions of Earth's atmosphere, the European Space Agency's Euclid Space Telescope represents a monumental leap in our ability to chart the invisible. Think of it as the most ambitious cartography project in human history, but its map won't be of lands and oceans. It will be a detailed three-dimensional chart of dark matter itself. Euclid will accomplish this by performing an ultra-high-resolution survey of the sky, measuring the subtle gravitational lensing, the warping of light from billions of galaxies with astonishing precision. By tracking how this distortion varies across the cosmos and throughout cosmic time, Euclid will allow scientists to create a dynamic map of how dark matter is distributed, how it clumps together, and how those clumps have evolved over billions of years. This data will be ruthlessly precise. It will test whether the cold dark matter model correctly predicts the statistical distribution of halos and filaments on the largest scales, or if the observations reveal unexpected wiggles and anomalies that could point toward self-interacting dark matter or even more exotic possibilities. The telescope's incredible sensitivity will also allow it to probe the very nature of dark energy, exploring the potential interplay between the two great cosmic unknowns. Meanwhile, in the profound silence of a former gold mine in South Dakota, the LUX Zeppelin experiment continues its patient, quiet vigil. LZ is the culmination of decades of refinement in the direct detection hunt, a vat of 10 tons of ultra-pure liquid xenon held at -100 degrees Celsius, watched over by arrays of exquisitely sensitive light sensors. Shielded from cosmic rays under a mile of rock, it waits for the impossibly rare event, a bump in the night. The goal remains to detect the faint recoil that would occur if a weakly interacting massive particle, a WIMP, were to collide with a xenon nucleus. LZ is so sensitive that its main background noise isn't from radioactivity on Earth, but from the constant rain of neutrinos from the Sun. This creates a fascinating threshold. If WIMP are lighter or interact more weakly than a certain point, their signal would be drowned out by the neutrino background, a phenomenon known as the neutrino floor. The ongoing silence from LZ and other detectors, like Xeno-NNT, is therefore not merely an absence of data. It is actively closing doors, systematically eliminating vast swaths of potential parameter space, and pushing the hypothetical WIMP into an increasingly narrow and fine-tuned corner of possibility. But the quest doesn't end with mapping and direct detection. A third critical front is opening up through the study of the universe's oldest light. Next-generation experiments like the Simons Observatory and the planned CMBS-4 are deploying armies of ultra-sensitive detectors in the high, dry air of the Chilean Andes to scrutinize the cosmic microwave background with unprecedented detail. While the Planck satellite gave us a spectacular baby picture of the universe, these new observatories are like giving that baby a full MRI scan. They will look for incredibly subtle patterns in the polarization of this ancient light, patterns that are imprinted by gravitational waves from the universe's inflationary first moments. The precise characteristics of these patterns are exquisitely sensitive to the fundamental ingredients of the cosmos. By measuring them, scientists can perform a stringent test on the entire standard model of cosmology. Any significant deviation from what lambda CDM predicts could be the first hint of entirely new physics, perhaps even evidence supporting a modified theory of gravity that operates on the largest scales. These observatories are not looking for dark matter itself. They are stress-testing the very framework that requires it. The beautiful synergy of this approach lies in its ability to corner the truth from all sides. Euclid's large-scale maps, LZ's underground silence, and CMB-S4's primordial snapshots will generate a tsunami of data within the next 5 to 10 years. This data won't just provide incremental updates. It has the potential to be genuinely transformative. The most likely outcome is that one of these paths will yield an unambiguous discovery, a definitive particle detection, or a clear signature in the sky that confirms a modified theory of gravity. However, the most thrilling possibility is that all the data will come together to deepen the mystery further, revealing inconsistencies that none of our current models can explain. This would not be a failure, but the ultimate success of science, forcing us to abandon comfortable assumptions and compelling the next Einstein or Verlin to conceive of a radically new conception of reality. The coming decade promises to be a golden age of cosmological discovery, a period where our fundamental understanding of the universe's hidden architecture is either cemented or completely rewritten. Yet for all the compelling evidence we've explored, the public conversation around dark matter often gets flattened into a misleadingly simple narrative. Popular science documentaries and headlines, in their well-intentioned effort to make complex ideas accessible, frequently present dark matter as a done deal, a mysterious substance we're just one experiment away from boxing up and putting on a shelf. This oversimplification creates a cascade of misconceptions, leaving many with the impression that dark matter's existence is a proven, ironclad fact, and that any scientists questioning it are operating on the radical fringes. Nothing could be further from the vibrant, contentious, and wonderfully uncertain reality of how cosmology actually works. The truth is, science doesn't progress by declaring eternal truths. It advances through a continuous process of debate, doubt, and rigorous challenge. Dark matter isn't a closed case, it's one of the most spectacular examples of a scientific theory in flux, a living, breathing mystery that is actively being rewritten. This gap between public perception and scientific practice leads to some common misunderstandings. One of the most persistent is the idea that dark matter has been definitively proven. In reality, the scientific community doesn't deal in absolute proof. It deals in evidence and confidence. What we have is an overwhelming amount of gravitational evidence that something is out there, influencing galaxies in ways that cannot be explained by known matter and known laws. We've given that gravitational effect the name dark matter, but labeling the phenomenon is not the same as identifying the cause. It's the difference between knowing a crime has been committed and knowing exactly who the perpetrator is. We have the cosmic fingerprint, but we're still running it through the database. This is why the decades-long, fruitless search for a direct detection particle is so scientifically valuable. It's the process of trying to match the fingerprint to a suspect. Another frequent misconception is that modified gravity theories like MOND are simply the work of a few stubborn outsiders refusing to accept the consensus. This framing misses the point entirely. Good science doesn't have sacred cows. Every idea, no matter how established, must withstand relentless scrutiny. Alternatives like MOND are not a nuisance. They are a vital part of the scientific process. They act as a necessary counterweight, constantly testing the dominant paradigm and forcing its proponents to sharpen their arguments, refine their models, and account for every last anomaly. The very existence of a credible alternative theory makes the entire field stronger, as it prevents groupthink and ensures that the dark matter hypothesis is continually stress-tested. The goal isn't for one side to win, but for the entire community to arrive at the most accurate description of the universe, wherever that may lead. This is why fostering a more nuanced public discourse is so crucial. When we present science as a list of settled facts, we rob it of its drama and its humanity, the very elements that make it so exciting. The real story isn't a boring recitation of what we know. It's the thrilling detective story of how we're trying to find out. By clarifying what is solidly known, the gravitational evidence from rotation curves and lensing is undeniable versus what is still speculative. The exact nature of the particle, if it even is one. We empower everyone to engage with the authentic adventure of discovery. Understanding that a scientific theory is a model, a best-fit explanation based on current data that is always subject to revision, is liberating. It means that new findings from JWST or unexpected results from Euclid aren't signs that science is broken, but that it is working exactly as it should, constantly evolving and self-correcting. Ultimately, appreciating this process allows us to fully engage with the profound questions at the heart of cosmology. The debate over dark matter versus modified gravity isn't just a technical argument about astrophysics. It's a fundamental inquiry into the nature of reality itself. Are we living in a universe dominated by unseen, exotic matter, Or are we on the cusp of discovering that our understanding of gravity, one of the most familiar forces, is fundamentally incomplete? By moving beyond oversimplified narratives and embracing the beautiful complexity and healthy uncertainty of active research, we don't just become better informed viewers, we become participants in one of the greatest intellectual journeys in human history, a collective effort to read the hidden pages of the cosmic story. Yet beyond the telescopes and underground labs, beyond the equations and simulations, lies a deeper layer to this quest, one that touches on the very nature of knowledge itself and our place in the cosmos. If dark matter is not a simple particle, if the foundational story we've told for decades requires a fundamental rewrite, the implications ripple far beyond the pages of astrophysics journals. They challenge our philosophical and ethical frameworks, forcing us to confront what it means to live in a universe that is far less settled than we might have assumed. This isn't just about updating a textbook entry. It's about navigating a shift in our collective understanding of reality, a process that carries profound responsibilities. Consider the immense public trust and investment placed in large-scale scientific endeavors. Projects like the James Webb Space Telescope, the Large Hadron Collider, and the upcoming Vera-C. Rubin Observatory represent some of the most ambitious and costly scientific enterprises in human history. They are funded by societies that make deliberate choices about how to allocate finite resources for the pursuit of knowledge. These choices are based on a consensus view of what is most likely to yield discovery, a consensus built upon the prevailing paradigm of cold, dark matter. If that paradigm were to be overturned, it would inevitably raise difficult questions. Did we invest billions correctly? Could those resources have been better directed toward alternative theories or different technological approaches? This is not a critique of science, but a recognition of its deeply human context. The process of science is not conducted in a vacuum. It is a societal endeavor, and its direction is shaped by our best judgments, which are sometimes, as history shows, our best misjudgments. This potential for paradigm shifts also carries a significant ethical weight in the realm of education and public understanding. For a generation, students have been taught that the universe is primarily composed of dark matter and dark energy. This model provides a coherent, if incomplete, narrative for how the cosmos works. To dismantle that narrative risks creating a crisis of confidence, not in science itself, but in the way scientific knowledge is communicated. If the public perception is that scientists keep changing their minds, it can erode the vital trust that enables long-term, risky research. The challenge, therefore, is to communicate the dynamic, evolving nature of scientific inquiry not as a flaw, but as its greatest strength. We must celebrate the uncertainty, framing new discoveries not as admissions of failure, but as thrilling evidence that the scientific process is working exactly as intended, constantly refining, questioning, and inching closer to a more truthful picture. Furthermore, rethinking our most fundamental physical laws forces a philosophical reckoning with humility. For centuries, humanity has progressively displaced itself from the center of the universe, from the Copernican revolution to the understanding that we orbit an average star in a common galaxy. Each step was a blow to our cosmic ego, yet each also expanded our appreciation for the grandeur of reality. A discovery that forces us to rewrite gravity or matter itself would be the ultimate extension of this trend. It would be a powerful reminder that our models of the universe, however elegant and mathematically sound, are ultimately approximations, maps that help us navigate a territory far more complex and mysterious than we can currently conceive. This humility is not a weakness. It is the essential mindset for true exploration, protecting us from the hubris of believing we have finally figured it all out. Ultimately, the ethical dimension of this search calls for a balanced approach, a steadfast commitment to following the evidence wherever it leads, coupled with a thoughtful consideration of the broader impact of that journey. It requires scientists to be not just brilliant researchers, but also thoughtful communicators and stewards of public trust. It asks society to maintain the courage and patience to fund fundamental research whose ultimate payoff is unknown, valuing the pursuit of understanding for its own sake. As we stand on the precipice of potentially revolutionary change, we are reminded that science is more than a collection of facts. It is a values-driven process of inquiry. The choices we make now, which theories to pursue, which experiments to fund, how to explain the uncertainties, will shape not only our future understanding of the cosmos, but also the relationship between humanity and the vast, mysterious universe we are striving to comprehend. Sometimes the most profound secrets of the cosmos are hidden not in the distant light of a quasar, but in the intricate patterns of the world right here at our feet. To truly grapple with a mystery as vast as dark matter, we must be willing to look beyond the traditional boundaries of physics and astronomy, drawing inspiration from the entire tapestry of human knowledge. The fields of biology and chemistry, in particular, offer a treasure trove of metaphors, models, and ways of thinking that can jolt our cosmological imaginations out of well-worn ruts and into entirely new landscapes of possibility. Consider one of the greatest unsolved puzzles in all of science, the nature of consciousness. From a purely reductionist perspective, the human brain is just a collection of ordinary atoms and molecules, no different from the stuff that makes up a rock or a star. And yet, from the intricate networking of billions of neurons, something entirely new and unexpected emerges. A subjective experience, a sense of self, the phenomenon of thought. This is what philosophers call an emergent property, a complex behavior or quality that arises from a system that cannot be predicted or explained simply by studying its individual components in isolation. The whole becomes not just greater than, but fundamentally different from, the sum of its parts. This biological concept of emergence is now sparking a revolution in how some physicists think about gravity itself. For centuries, we've treated gravity as a fundamental force, an innate property of mass woven into the fabric of space-time. But what if, like consciousness emerging from neurons, gravity is not fundamental at all? What if it is an emergent phenomenon, a collective behavior that arises from the countless quantum interactions happening at the very smallest scales of reality? In this view, the force that holds galaxies together and bends the path of light doesn't originate from a fundamental field, but condenses out of the statistical churn of the universe's underlying information, much like the concept of temperature emerges from the random motion of molecules. This radical perspective, inspired by biology, could potentially explain the effects we attribute to dark matter without needing to invoke any particles at all, reframing it as a subtle change in how gravity behaves in the cosmic hinterlands. The world of chemistry provides another powerful lens, offering stunning examples of self-organization. In a famous experiment known as a Belousov-Zhabotinsky reaction, a simple mixture of chemicals in a Petri dish can spontaneously generate breathtakingly complex patterns, concentric rings, swirling spirals, and pulsating waves that seem almost alive. This order doesn't come from an external blueprint or a hidden designer. It emerges spontaneously from the feedback loops and non-linear interactions between the molecules themselves. The system organizes itself, finding an elegant order within its own inherent physics. Now transpose this idea to a galactic scale. Could the majestic spiral arms of a galaxy and the vast web of cosmic filaments be the universe's own version of a Belousov-Zhabotinsky reaction? Perhaps the intricate structures we see are not solely sculpted by the gravitational pull of an invisible substance, but are instead the result of complex, self-organizing processes within the visible gas, dust, and magnetic fields. The gravitational dynamics we observe might be the outcome of a system naturally tending toward organized complexity, not unlike a chemical solution settling into a stable, patterned state. This doesn't eliminate the need for dark matter, but it opens the door to models where its role is more nuanced, interacting with visible matter in a cooperative dance of self-organization rather than acting as a lone, dominant architect. These cross-disciplinary connections are far more than just poetic analogies. They are a vital intellectual lifeline. The history of science is littered with breakthroughs that occurred when someone dared to borrow a concept from an unrelated field. The structure of the benzene ring was revealed to Auguste Kekulé in a daydream about a snake eating its own tail. The foundations of seismology were advanced by studying the propagation of cracks in glass. By embracing this holistic, interdisciplinary mindset, we dramatically enrich our toolkit for cosmic deciphering. We allow ourselves to ask questions we wouldn't have otherwise considered. Could the universe have a form of metabolism? Is there a cosmic equivalent of an ecosystem? These questions might seem fanciful, but they break down the walls of conventional thinking, creating the conditions for the kind of paradigm-shifting insight that ultimately cracks open a mystery as profound as dark matter. The answer may not lie in a deeper tunnel within the mine of physics, but in a bridge we build to the forest of biology or the laboratory of chemistry. It's worth remembering that some of the most profound revelations in science didn't come from a carefully plotted path on a whiteboard, but from a fortunate stumble in the dark. The history of discovery is filled with glorious accidents: the unexpected mold that led to penicillin, the persistent static hiss in a radio antenna that turned out to be the echo of the Big Bang itself, the cosmic microwave background radiation. These weren't the results of targeted experiments proving a hypothesis. They were moments of brilliant serendipity, where a prepared mind recognized the significance of something they weren't even looking for. This pattern suggests that the ultimate solution to the dark matter enigma might not emerge from the multi-billion-dollar detector we built specifically to find it, but from a completely unrelated experiment, an anomalous blip in the data that everyone else ignores, or an astronomical observation that seems to make no sense at first glance. Consider the possibilities. A team of particle physicists at the Large Hadron Collider might be analyzing the debris from a proton collision, searching for signs of supersymmetry, when they notice an unusual energy signature that defies all predictions of the standard model. This tiny, unexpected spike in the data could be the first hint of a particle that constitutes the dark sector, or radio astronomers mapping hydrogen gas in a distant galaxy might detect a faint, anomalous signal at a very specific frequency, a signature of decaying sterile neutrinos that has been hiding in plain sight. Even a deep space probe on a mission to study the solar wind could stumble upon the answer, perhaps by measuring an unexpected flux of particles streaming from the center of our galaxy that points directly to the properties of weakly interacting massive particles. The clue that finally cracks this 80-year-old case is likely to be something we aren't actively searching for, a piece of the puzzle we didn't even know was missing. This long history of fortunate accidents argues powerfully for the vital importance of curiosity-driven, blue-sky research. When we channel all of our resources solely into testing the most popular theory, we risk building a collective blindness to anything that falls outside that narrow expectation. The most transformative discoveries often come from projects that were deemed too speculative or too fringe. from scientists who are simply following their fascination with a peculiar phenomenon without a clear practical application in mind. Funding this kind of open-ended exploration is not a luxury. It is an essential investment in the unexpected. It's the reason we build telescopes that can survey the entire sky, not just stare at predetermined targets, and why we encourage physicists to analyze old data with new questions. The next key to understanding dark matter might be buried in a dataset that was collected for a completely different purpose 10 years ago, waiting for the right person with the right idea to come along and ask a new question of it. Ultimately, this role of chance serves as a profound humbling agent. For all our grand theories, our sophisticated simulations, and our complex detectors, nature retains the final say in how and when it reveals its secrets. We can plan and predict, but the universe often delights in the surprise twist. This isn't a failing of the scientific method, it's its greatest strength. The process is designed to be responsive to surprise, to adapt to the unexpected data point that forces a paradigm shift. As we continue this cosmic detective story, we must cultivate a mindset that not only tolerates anomalies but actively celebrates them. The strange galaxy that doesn't fit the pattern, the particle detection that makes no sense, the gravitational lensing that is slightly off, these aren't frustrations to be explained away. They are the most exciting clues we have, the whispers from the universe that we are on the verge of learning something truly new. The solution will likely come when we least expect it, reminding us that the journey of discovery is not a straight line, but a winding path full of beautiful, unforeseen turns. And so we find ourselves at the end of this cosmic journey, but it is an ending that feels much more like a beginning. We started with a story that seemed so certain. The universe is held together by an invisible, mysterious substance called dark matter, a sea of sluggish particles that provides the gravitational glue for everything we see. It was an elegant solution, a fix that preserved our cherished laws of physics while accounting for the strange motions of galaxies. For decades, this was the established narrative, the comfortable consensus that filled our textbooks and guided our research. But as we ventured deeper, that certainty began to unravel, revealing a mystery far more profound and exciting than we ever anticipated. We encountered radical alternatives like modified Newtonian dynamics, which asked the breathtakingly simple question: what if we don't need new matter, but a new understanding of gravity itself? We explored the mind-bending possibilities of a dark matter superfluid, whose quantum vibrations could mimic the effects of MOND on a galactic scale while behaving like standard dark matter across the cosmos. We even peered into the quantum foam of empty space itself, considering that the answer might lie not in a particle, but in a deeper, emergent nature of gravity and spacetime. Each of these ideas is not just a fringe theory. They are serious, rigorous responses to the growing cracks in the standard model. From the historical puzzles first spotted by Zwicky and Rubin to the JWST's stunning revelation of galaxies that grew up far too fast, every new piece of evidence has complicated the picture rather than simplifying it. The discovery of galaxies that seem to have no dark matter at all struck a direct blow at the idea that it is a universal necessity. The stubborn, deafening silence from deep underground detectors has pushed the most popular candidate particles into narrower and narrower theoretical corners. And the Hubble tension, that glaring discrepancy in the universe's expansion rate, stands as a monumental warning that our entire cosmological model might be missing a crucial ingredient. We are no longer simply searching for a hidden particle. We are questioning the very framework of our reality. What has become undeniably clear through all of this is that our universe is far stranger, more complex, and more wonderfully mysterious than we could have imagined just a few decades ago. The cosmos is not yielding its secrets easily. It is presenting us with contradictions and anomalies that are forcing a true renaissance in cosmological thought. The path forward is not a straight line to a single answer, but a branching tree of possibilities, each with its own compelling evidence and its own formidable challenges. As this research accelerates with powerful new tools like the Hubble Space Telescope and the Vera Rubin Observatory, we must be prepared for any outcome. We may be on the verge of finally detecting a dark matter particle, confirming one chapter of the story, or we may be forced to completely rewrite the textbooks, embracing a new law of physics that redefines gravity and matter as we know it. This is not a sign of failure, but the exhilarating sound of science working at its absolute best, questioning, testing, and evolving in its relentless pursuit of truth. Thank you for joining this incredible exploration of the unseen forces that shape our cosmos, a journey from seeming certainty into a deeper, more beautiful mystery. If you've enjoyed pondering these cosmic questions with us, please show your support by liking this video and subscribing to the channel for more journeys to the edge of understanding. We'd love to hear your thoughts on this grand puzzle. Which explanation for dark matter do you find most compelling? Share your perspective in the comments below.